Have you ever wondered what it feels like to wait 45 minutes just to see if a tiny change you made to your code actually works? Imagine the sheer mind-numbing frustration. You're a brilliant engineer at one of the world's most innovative companies, a place that prides itself on speed and efficiency. Yet you're stuck in a digital traffic jam, watching a progress bar crawl across your screen. Your flow is broken, your creativity is stifled, and your productivity is bleeding away, minute by agonizing minute. This wasn't some hypothetical nightmare. This was the daily reality for engineers at Google in the mid-2000s. It was a problem of scale. It's a problem of complexity, and a problem that was slowly grinding the gears of progress to a halt. It was out of this shared, simmering frustration that an idea was born, not just a solution, but a rebellion. A rebellion that sparked the creation of a new programming language, one designed from the ground up to be fast, simple, and incredibly scalable. They called it Go, and it would go on to quietly change the very foundation of how the modern internet runs. The story of Go begins at a pivotal moment in the history of computing. For decades, the tech industry had been riding a wave of relentless progress driven by Moore's Law. Processors were getting exponentially faster year after year, meaning our software would magically speed up without us having to do much. But around the mid-2000s, that free ride came to an abrupt end. The laws of physics had caught up with us. We couldn't cram any more transistors onto a chip without it melting. So instead of making a single processor core faster, manufacturers started adding more cores. The era of the multi-core processor had arrived, and with it, a monumental challenge. The dominant languages of the time, titans like C++ and Java, were born in a single-core world. They weren't naturally equipped to handle this new paradigm of concurrency, of doing many things at once. Writing concurrent code in these languages was notoriously difficult, a minefield of race conditions, deadlocks, and other obscure bugs that could drive even the most seasoned developers to despair. It was like trying to conduct a symphony orchestra where every musician played from a different sheet of music. The potential for chaos was immense, and the tools at hand just weren't built for the job. This shift didn't just affect hardware, it fundamentally broke the assumptions upon which decades of software had been built. This hardware revolution collided head-on with another crisis unfolding inside Google's walls, a crisis of scale. The company's projects had become behemoths. We're not talking about thousands of lines of code, we're talking about millions, sometimes tens of millions, woven together in a sprawling, intricate web. These massive code bases were a labyrinth of endless dependencies, where one small change could trigger a cascade of unforeseen consequences across the entire system. And then there were the compile times. The very act of turning human-readable code into something a computer could execute had become a productivity-draining black hole. Waiting 45 minutes for a build to complete wasn't just an inconvenience, it was a creativity killer. It yanked engineers out of their state of flow, that deep, focused concentration where real innovation happens. The tools they were using, powerful as they were, had become part of the problem. They were complex, feature-heavy, and slow, designed for a different era of software development. A fundamental disconnect had emerged between the work that needed to be done and the tools available to do it. The system was straining under its own weight, and it was clear that a new approach was desperately needed. It was in this environment of frustration and bottlenecking that three legendary figures of computer science decided they had had enough. These weren't just any engineers. They were the architects of the digital world as we know it. There was Ken Thompson, the co-creator of the Unix operating system and the C programming language, the very bedrock of modern computing. There was Rob Pike, a key member of the original Unix team at Bell Labs, and a pioneer in distributed systems and computer graphics. And there was Robert Griesemer, a brilliant mind who had worked on Java's Hotspot virtual machine and Google's own V8 JavaScript engine. In late 2007, while waiting for yet another massive C++ build to compile, they began sketching out the principles of a new language on a whiteboard. Their goal was audacious in its simplicity. They didn't set out to create the world's most powerful or feature-rich language. They wanted to do the opposite. They wanted to build something leaner, smarter, and fundamentally simpler language that would get out of the developer's way and let them focus on solving problems. It was a conscious step back from the more is more philosophy that had dominated language design for decades. They envisioned a language for the new era of computing, one that was built for massive code bases, multi-core processors, and networked environments. The design philosophy behind Go was a radical departure from the norm, crystallized in a clear, unwavering principle: fewer features, done better. This wasn't about stripping away power, it was about surgically removing complexity. Every single element of the language was scrutinized, and if it didn't serve a clear, essential purpose, it was left out. They wanted to create a language that was easy to learn, easy to read, and most importantly, easy to reason about, even at a massive scale. It was a minimalist manifesto for software engineering. The language would feel familiar to C-style programmers, but would be unburdened by the decades of accumulated baggage that had made languages like C++ so notoriously complex. The focus was on clarity and orthogonality, ensuring that a small set of simple, well-designed features could be combined in powerful ways, rather than providing a kitchen sink of specialized, overlapping tools. This pursuit of simplicity was not an aesthetic choice. It was a pragmatic one, born from the painful experience of maintaining millions of lines of overly complex code. This philosophy manifested in some bold, and at the time, controversial design decisions. Go famously ditched the concept of inheritance, a cornerstone of traditional object-oriented programming that had often led to rigid and confusing class hierarchies. In its place, it embraced a more flexible and powerful idea: composition, through a feature called interfaces. This allowed developers to build complex behaviors by combining smaller, independent pieces like snapping together Lego bricks. The syntax itself was ruthlessly simplified, removing unnecessary parentheses, semicolons, and keywords, making the code cleaner and less prone to errors. But perhaps one of the most brilliant and deceptively simple innovations was a tool called guft. This command line utility automatically formatted all Go code to a single canonical style. Just like that, it eliminated an entire category of pointless, time-wasting arguments that have plagued development teams for decades: the petty debates over tabs versus spaces, or where to place curly braces. By making code formatting a non-issue, the creators of Go refocused the conversation on what truly matters: the logic and quality of the software itself. While simplicity was its foundation, concurrency was Go's superpower. The designers understood that mastering the multi-core world was the key to future performance. Instead of bolting on complex threading libraries like other languages, they built concurrency directly into the heart of the language itself, with two elegant, powerful concepts: goroutines and channels. Goroutine is an incredibly lightweight thread of execution, so lightweight that you can easily run hundreds of thousands or even millions of them at once. Starting one is as simple as putting the keyword Go in front of a function call. Channels then act as the communication pipelines between these goroutines, allowing them to send and receive data safely without the risk of the race conditions that plague traditional multi-threaded programming. This model, inspired by a formal computer science concept called communicating sequential processes, CSP, transformed one of the most difficult areas of programming into something intuitive and accessible. It made parallel programming simple, safe, and even enjoyable, turning the complex art of multi-threading into a tool that any developer could confidently use to build incredibly fast and responsive applications. Beyond concurrency, Go tackled another chronic source of pain for developers: the nightmare often referred to as dependency hell. In many ecosystems, managing the web of external libraries and packages that a project relies on can be an incredibly fragile and complex task. Different versions conflict, dependencies have their own dependencies, and the whole house of cards can come tumbling down with a single update. Go's solution was elegant and decisive. It introduced a powerful and simple build system that compiles everything the application, code and all of its dependencies, into a single static binary file. This one file contains everything needed to run the program on a target machine, with no external libraries or runtime environments required. This approach not only solved the dependency management problem, but also made deployment incredibly straightforward. And, true to its founding principles, the compilation process itself was astonishingly fast. The fast build times weren't just a convenience. They were a core feature designed to keep developers in a state of creative flow, allowing them to iterate quickly, test ideas, and build software at the speed of thought. When Google officially released Go as an open-source project in November 2009, it was met with a mix of curiosity and skepticism. But it didn't take long for the development community to recognize its power. Early adopters were drawn to its simplicity, its blazing fast performance, and its pragmatic approach to solving real-world problems. The language quickly found a perfect home in the burgeoning world of cloud computing and infrastructure tooling. A small startup called .cloud, which would later become Docker, used Go to build its revolutionary containerization platform, which fundamentally changed how software is packaged and deployed. Soon after, Google itself used Go to build Kubernetes, the node-dominant platform for orchestrating and managing containerized applications at a massive scale. Suddenly, Go was everywhere. It became the unseen engine powering much of today's cloud infrastructure, from web servers and databases to monitoring systems and command line tools. It had quietly become one of the most important languages of the internet, the unsung hero behind the services we rely on every single day. What started as an act of rebellion, a frustrated response to unnecessary complexity and wasted time, had blossomed into a global movement. Go's success proved that there was a deep, unfulfilled hunger in the software world for clarity, for performance, and for a more practical, pragmatic approach to engineering. It challenged the long-held belief that a language had to be complex to be powerful. It demonstrated that by carefully curating a small set of well-designed features, you could empower developers to build robust, scalable, and maintainable systems more effectively than ever before. The story of Go is more than just the story of a programming language. It's a powerful lesson in the value of simplicity, the importance of focusing on the developer's experience, and the incredible things that can happen when you have the courage to question the status quo and build the tools you wish you had. It is a testament to the idea that sometimes the most revolutionary act is not to add one more feature, but to take one away.